So hello everyone, I hope that you are doing well. This presentation is about current trends of massive MIMO millimeter waves on wireless systems. I want to present some of the current trends at different research levels for physical layer to system layer analysis as well. So let's get started. So the first aspect to be considered is the millimeter wave channel, its characteristics, and the current knowledge we have about it. So one of the main issues in frequencies above 6 GHz is the large path loss, which can be compensated by directional antennas. And several papers assume that such directivity is already provided when resources are assigned among different devices over time, frequency, and space. Another important characteristic is the fact that two propagation laws arises, line and no line of sight, and depending on the distance between the transmit and receive devices, we can consider the presence of one or both path components. For instance, indoor models consider strong line of sight component, whereas outdoor links are compounded by a number of no line of sight paths. When we have a dominant line of sight component, we may suffer from strong shadowing from small objects, walls, or the human body itself, which may result in high losses of power and high outage probability. At millimeter wave, we can have a large scale antenna rise that can be encapsulated in a chip, and this means that massive MIMO is or will be assumed at these high frequencies. Nevertheless, regardless of the number of antennas at both ends of the link, at millimeter waves we will observe that the multipath components arrive in clusters, and the number of clusters is usually small. This means that under certain conditions, the millimeter wave channel will be sparse, and standard signal processing for massive MIMO must consider low-rank channels, especially for massive MIMO scenarios. Another aspect that is present in the current literature is the modeling of the SINR, which takes into account the physical properties of the antennas, such as the pattern or geometry, as well as the directivity. For signal processing, we need to know the angles of departure and arrival per link. Either instantaneous or statistical knowledge is assumed. So it is important to notice that the aim of millimeter waves is to increase the operation bandwidth, but such bandwidth is also increasing the noise, and this should be considered when modeling the system, and is already considered in several papers. And there are two physical phenomena that are tightly related to directivity and may negatively affect the performance. On the one hand, we have blockage, which occurs when there is an object in the line of sight path. In millimeter waves, the losses due to absorption are orders of magnitude higher than in microwaves, and if the channel has a small no line of sight component, the connection will be lost. On the other hand, deafness occurs when the transmit and receive beams are not aligned. If the beams are not aligned, then we can achieve large channel gains, and the probability that other beams create interference is very small, almost negligible. Therefore, many papers present system models that are noise limited rather than interference limited. And the main issue is a mismatch between the beams can degrade the performance drastically. And such a mismatch may occur due to the outdated or corrupted channel information or drastic changes in the medium due to mobility. So one way to overcome the blockage and deafness is by recalibrating the beams periodically. And this is tracking the best beams over a transmission period and refining the beams towards the directions with the strongest channel magnitude. So defining the beams is a process that requires resources. For instance, within a frame of duration t, we will dedicate a fraction tau to find the beams. And the value of tau highly depends on how narrow the beams are, which in practice means that we use or more or less code words to quantify the angular domain. In the literature of radio resource management, and in particular the research focused on heterogeneous networks, currently there is a discussion about using both millimeter waves and microwaves for cellular communications. So on the one hand, bandwidth in millimeter waves can be used to achieve a very large data rate. On the other hand, microwaves can provide a reliable and robust transmission of control and signaling messages, which require small or moderate transmission rates. So this concept is also referred to as decoupling the control and user planes. A related concept is the fallback trade-off, where control and user planes occur in the same frequency band, but such a band changes from microwave to millimeter wave and vice versa according to the measured signal strength in each band, and this can be thought as a dynamic band switching. Currently, there is no standardization for the coexistence of millimeter waves and microwaves on cellular networks. However, different bands provide adequate characteristics regarding multipath and acceptable performance in no line-of-sight scenarios. And the candidate bands for cellular networks are the 28, 39, and 72 GHz, and they have been heavily explored in field trials for outdoor communications, especially in the US. Due to the coverage provided by millimeter waves and the channel characteristics, cellular networks will require advanced deployments of base stations. Moreover, the cellular network must have two characteristics, roaming and reuse, and the former is related to mobility and handover management, whereas the latter has to do with delivering a target quality of service and mitigating interference. Some of the main services for this kind of deployments may be backhaul network, either in-band or out-band, and small cells, delivering one or two streams per user. Resource management is a huge field, and it covers topics from the physical and the media access control layers. One function of the MAC layer is to associate the users with a particular base station and to assign resources to them, which is known as scheduling. For millimeter waves, and especially for massive MIMO configurations, we know that the number of simultaneous users per resource depends on the number of RF change at the base station. The association of the users usually depends on the signal strength, but other metrics can be used, such as the quality of service or traffic load. In heterogeneous networks, the power of the macro base stations can shadow the power of small cells. Therefore, some techniques bias the user association process to balance traffic in the network. And it's important to bear in mind that user association and scheduling are both hard problems to solve, and there is always a trade-off between the complexity and optimality of the algorithms that solve such problems. Once the users have been associated to a base station, we need to find the beamformers, and to do that we rely on channel state information, and we can estimate a channel by the uplink downlink reciprocity, as in TDD, or we can use pilot signals and statistics of the channel. In practice, we also use codebooks to quantize either the channel or the preferred beamformer and send that information to the transmitter. And bear in mind that multi-user MIMO are very sensitive to synchronizations and channel state information. One important source of interference that may affect user association is the fact that common channels are used by several base stations for signaling and for channel estimation, which limits the overall network performance. Interference can be mitigated in a number of ways, and the easiest way is to assign orthogonal resources to each user. But such an approach may not be the best choice, especially in heterogeneous networks where the powers and traffic loads, user density, and other parameters are not the same across the transmitters. Therefore, we must find a balance between centralized and distributed schemes to combat interference that can be reliable and scalable with the size of the network. So in multi-user MIMO system, the steering matrix or beamformer is computed from explicit channel state information, and this means that the transmitter sends some known symbol sequences per antenna until the receiver can construct the entire channel matrix. So the estimated channel is compressed and sent back to the transmitter. So considering a massive MIMO setting, it is common in the mmWave literature. And since we know that the channel is sparse and compounded by few clusters, techniques for compressed sensing can be used. Now, for conventional multi-user MIMO, where there are 4 or 8 antennas at the transmitter, it is feasible to implement full digital beamforming, since each antenna element has its own RF chain. And this means that the schemes such as zero forcing or singular body decomposition can be used to invert the full rank channel. However, in massive MIMO settings, the number of RF chains is less than the number of antennas at the transmitter, and the most accepted approach in the literature is known as hybrid beamforming, where digital and analog beamforming techniques are combined to define the massive MIMO steering matrices. Now, the optimal structure of hybrid beamforming is still an open problem, and current research is focused on designing different transceiver architectures to achieve the same performance of the full digital beamforming, but using hybrid beamforming. For standardized technologies such as Wi-Fi, the procedure to find the steering matrix are well known, and the challenge arises for directional antenna systems, which affects the granularity of the codebook that quantizes the spatial domain. In these scenarios, the current literature is focused on designing fast algorithms to set and refine the steering directions. This figure from a recent IEEE Wireless Communication magazine illustrates different hybrid architectures for massive MIMO scenarios. It is worth mentioning that the performance of the hybrid beamforming highly depends on the channel characteristics. Wireless backhaul applications seems to be appropriate for these architectures, since channel estimation errors due to mobility or Doppler effect do not degrade the performance. So, to illustrate the concept of massive MIMO and millimeter waves, let's consider different parameters to describe a wireless scenario. In a multi-user scenario, the peak rate is a common metric to assess performance. And notice that the rate depends on the percentage of time devoted for channel estimation, in this case is the variable tau, and the signal to interference plus noise ratio, or SINR. Now, the SINR is a function of the type of beamforming that is implemented. In this particular case, the expressions use fully digital schemes, zero forcing and conjugate beamforming. Now, one important parameter previously mentioned is the spatial load, which is the ratio between the number of transmitted streams over the number of RF chains in the system. So for this example, we will assume that MJ is the total number of RF chains per transmitter. So the SNR decreases with inter-user interference and pilot contamination, and the latter arises when the same pilot sequence is used by several base stations in the network, which negatively affects channel estimation. And finally, the channel gain in massive MIMO scenarios only depends on slow fading, and this is path loss and shadowing. In these expressions, it is assumed that the fast fading component vanishes for a large value of MJ. However, to include the millimeter wave component, one must scale the channel gain according to the directional antenna beams, and the beam width is a function of the angle of departure and arrival and the particular geometry of the antenna array. So recently, some authors have discussed the access mechanism at the millimeter wave for cellular and wireless LAN networks. Let's take an example of the requirements in the physical control channel. So the first step to establish a connection is to find the closest transmitter or access point. In cellular networks, for instance, There are common channels which carry the cell ID synchronization signals that are used for user association. So the directional antennas play an important role to model and calculate the received signal strength, or the SANR. As mentioned previously, the energy conveyed to the users depends on the antenna array and beam width. After user association, different parameters must be exchanged through the control channel. It is worth noticing that for decoupled user control plane or dynamic band switching, it is necessary to estimate the channels in both the microwave and mmWave communication. For long-range communication, we use the random access mechanism. Consider the IEEE 802.11ad, for instance. One critical problem identified in the literature is the waste of resources due to deafness. When one user cannot find its access point, it would take a long time backing off and retraining the beam directions. So there are many open problems for mobility and resource management at the mmWave level. If we consider a cellular or heterogeneous network operating at mmWaves, we know that the coverage of the base stations will be few hundred meters, and user mobility may create a serious waste of resources due to short coverage and handover. So an expected problem is to have unbalanced load at the base stations. User association based on signal strength may not be efficient if many users are geographically co-located. This is a well-known problem in cellular networks already. For instance, in big events like a football game or any other big event, people may have strong received signal, but there are no resources to serve all users. Another issue due to mobility is delay. So depending on the density of transmitters, it may take a long time to perform user association and channel estimation. So one alternative to mitigate handover and delays effect is to centralize the control and management of adjacent base stations, a concept known as cloud cell, which may reduce the latency and delay effects. And to improve the robustness for mobility, several base stations can be assigned to one user, but only one base station transmits data streams. This multiple association may allow fast handover and reduce the time for synchronization, but it requires a centralized network architecture. For ultradense networks, some of the main problems are to define which base stations should be coordinated and which one should be turned on or off, so that interference is reduced, load balance is achieved, and energy efficiency is maximized. As you can imagine, this is a very complex problem, hard to solve theoretically and even harder to solve in practice. And from the perspective of academic research, there are several works dealing with load balancing and user association. Based on user density, the base stations can cooperate to maximize coverage and reduce outage. Some theoretical works on heterogeneous networks define coverage regions based on the signal strength. However, there's a new trend that uses the traffic load to define the coverage regions. So the optimal association rules are to be defined for networks operating in microwaves and mmWaves as well. Some possible solutions to deal with load imbalance and reduce waste of resources are device-to-device communications or proximity services according to the 3GPP terminology. We have densification of small cells, in particular for indoor scenarios where data consumption is more critical and mobility is not an issue. And the integration of Wi-Fi and cellular communications, which is a promising solution to offload the cellular networks. In this presentation, we have covered some aspects of the mmWave channel. We talk about some candidate bands with nice multipath and non-line of sight properties for cellular communications. We mentioned some radio research management techniques and how they can be applied for millimeter waves. We saw that for cellular communications, beamforming and scheduling depend on channel estimation, geometry of antenna array, the transceiver architectures, and interference from adjacent cells. We described some of the main issues due to mobility and measure how centralized management can be used to avoid waste of resources and group base stations for coordinated operation. Finally, we mentioned some of the most promising techniques to achieve load balance in heterogeneous networks. At the end of the presentation, you can find a list of very useful references about massive MIMO, millimeter waves, and resource management. This is the end of the presentation, and I would like to thank you for viewing.